Okay, today's speakers is Ilan Hirshberg from Ben-Gurion University. So, and Ilan is going to talk about exotic circle actions on classifiable CSR algebra.
Yeah.
Yes, so please take the floor.
Yes, thanks, Ali. So, okay, so just to Stuart commented on my abstract. This classification program for nuclear C-star algebras is arguably nearly done. Where nearly done is the only small thing which is left is this.
The argument.
Yeah. Oh no, I mean I'm sure we will argue it. Okay, so we know that C-star algebras, so simple separable nuclear C-star algebras which satisfy the UCT are classified by the elegant variant provided they are Z-stable, they are regular, where there are several regularity properties which are equivalent. Let's say provided they are Z-stable. Z-stable meaning that they absorb tensorially the Lang's algebra. Okay, so the kind of remaining small issue which still has to be settled is whether the UCT automatically holds, but some people are working on it, so surely, like, you know, in a day or two we'll have an answer. But no, sorry, so that's a major open problem. But what we know now that there is some sort of dividing line, right, between the Z-stable case. I mean, if we want to go back a bit in history, I mean, let's say the Elliott classification program aimed at classifying simple separable nuclear C-star algebras. It took several decades until the first counterexample was constructed, right? That's due to Andrew Toms following some ideas of Jesper Willumsen. And it became later clear that basically the dividing line, or what's missing, is Z-stability. That there are some regularity properties. There are three ones conjectured to be equivalent: Z-stability, finite nuclear dimension, and strict comparison. One of those implications is not quite resolved yet. And then, you know, there was huge developments in classification which showed that, okay, that with this condition, which is the kind of C-star algebraic version of McDuff, we have classification, and without we don't know what's happening, right? I mean, we don't have classification, but we don't know what to do with it. So you somehow have this very crude map of the world of simple separable nuclear C-star algebras. We have the Z-stable, or let's say the regular case, or finite nuclear dimension, or whatever you want case, and we have the not Z-stable. Okay, so here, you know, at least they're classified. They're seen as somewhat nice. And what happens here? Well, we know there are examples. They're constructed. There's some idea. We roughly know how to construct those. Some of those, right? We have some essentially two constructions due to Willumsen, which give us ways of constructing all sorts of strange things here. And now you could proceed in several ways, right? You could just give those a bad name. Just say these are, you know, pathological or something. Like, we don't care about them. They're like bad, and just focus on those and move on and do something else with your life. Or you could just say that maybe those are just friends we haven't met, and we need to understand them better. They're just misunderstood. And part of the and I think that a good part of the question, or trying to figure out whether we want to, like, you know, understand those better or want to do something else, should be in how thick is this line, or how tall is this fence? I mean, I mean, is this like a reasonable world to live in, and these are just the scary monsters which we can live alone, or are there many holes in this fence and we can like easily move here? In which case, maybe we don't want to ignore the existence of these. Okay, so I guess the test question for this can be, or one test question would be, well, take one of those, do something which we consider reasonable to it, for example, form a cross product, and ask yourselves, do we still stay here, right? Because if this is a very robust class, whatever reasonable thing you do to it, which is not crazy, leaves you here, then maybe you could say, okay, let's ignore these, right? So the question, which is kind of a general question, which has been guiding several papers recently. I've been involved in some of them, other people have. Is this, let's suppose that A and whatever is there are called classifiable for short. Okay, and let's ignore the UCT question, because the UCT is, we don't know whether that's holds for all nuclear sister algebras, in particular whether the UCT problem is equivalent to the question of whether it's preserved under actions of finite groups or compact groups. So let's say that nice for classifiable will be everything else. So suppose A is simple, separable, nuclear, and Z stable. And suppose let's say G would be some amenable group. And alpha would be an action. Where if G is not discrete, and I mean it's point norm continuous, is the cross product does this satisfy the same property? Let's say I write Z stable because the other properties are basically reasonably well understood. The conditions which to ensure separable, we just need G to be second countable, and nuclear would be for whenever G is amenable, that would work. Simple, actually, there are some interesting questions there, but at least if G is discrete, that would follow if this action is pointwise outer. If G is locally compact abelian, that would follow if the action has what's called full strong con spectrum. I can define that if you want to, but and if G is locally compact, but not discrete, but not abelian, there is actually not clear what the answer is, and that's an interesting question. Okay. But okay, so let's suppose that we have an action such that is again simple nuclear, and let's say in the group, let's say second countable, just to remain in the separable world. The way you want to understand is this cross product Z stable. Okay, that's a good question, test question of how easy it is to jump over that fence. Okay. So let's list some known results in the discrete setting. So if G is the integers or a finite group, then yes, if the action has the Rossmann property, this was results myself and Wilhelm Winter. this would generalize to find Rochen dimension. I'm not going to talk too much about that. So it has versions with and without commuting towers. I'm not going to go into the distinction here. This was done first in this paper of myself, Winter and Zacharias. For the case of G is the integer defined groups, and there's defined groups. We have there's a result of was generalized in the paper of Sabo, Wu, and Zacharias to the case where G is virtually nilpotent. And discrete. And by Cordella for compact groups. In paper with Ilan Winter, Jean-Charles Wu, and Sabo. For the case of R. Okay, so this works assuming some sort of regularity property for the group action. We also know this goes back, at least for the case of Z, that goes back to that paper here with Winter and Zacharias, but and also for was generalized to the virtual nilpotent case, that the actions which have finite Rochen dimension are generic. They form a dense Lie delta set in the automorphism group, or in the set of actions. So it's a reasonably common property. For okay, I'll say that's generic. Okay, I won't go through all the groups, but for at least for those discrete settings. Okay, now there are also several papers which provide results that don't assume finite Rochen dimension, which go through strong outerness, which Rochen dimension would imply in those contexts. So further results, I mean, these results actually don't assume that A has to be simple. Okay, so assuming A is stably finite for n G is discrete, and the action strongly outer. Strongly outer means that whenever you take an invariant trace, you look at the GNS representation, you have an induced action on that following algebra. You want that action to be pointwise outer. Any invariant trace. Now, the induced action on this closure is pointwise outer. or what's called properly outer. It means a bit more because you don't want to have any corners on which it's inner. So here, let's list them. So if A is assuming this trace space is Bauer, and the extreme boundary is finite dimensional, Bauer means that this is a simplex and the boundary is compact. Then we know that we have the result assuming that G is arbitrary amenable, discrete amenable. And the action, right? If you have an action on A, it induces an action on pretty much anything associated to A. So on the trace space, on this extreme boundary, we want this to factor through a finite group action. So not the entire group action, but just the way it acts on traces. Actually, that's a paper with Gurdella and Andrea Vaccaro. And this generalizes results of I should put here of Matsui Sato and Sato. So we improve on their methods. Sato first proved that for Matsui Sato proves it when we have finitely many extreme traces. Sato proves it for the case where the action on this is trivial. So two same conditions on trace space. And G is integers, then it works for with no restriction. This is due to Lisa Wouters. And also, I'll put 2A and 2B, it's the same paper. And same conditions where G is virtually nilpotent. And the action on this extreme boundary is free. That's also due to Wouters, the same paper. Okay. The method there sure could be used for other things. The idea is basically you go back to this Rochel dimension paper. It's known that for action on abelian C-star algebras, free actions have finite Rochel dimension. And so somehow you use the fact that you could have finite Rochel dimension on this extreme, on the stratal picture and pull that back to a result on C-star algebra. It's a method which I'm sure we'll see more of. And three, it's a more recent preprint. This is only the result when the trace space is still Bauer, but there is no finite dimensionality assumption on the extreme boundary. So it has to be a compact measure space. So here, G is taken to be Z to the D, and the action is assumed to be free and minimal. So this is due to Rodella, Giffen, Hirshberg and Vaccaro. Okay. So I should point out there are no known counterexamples or conjecture counterexamples in the case where we have a discrete group action. I'm still not sure what's the right, if it's reasonable to conjecture that this is preserved. I mean, this gives some evidence, but maybe not quite enough. So who knows? But it's certainly an important question. So the theorem I want to discuss now, it's in some short preprint I put out last month, is that we have a negative result for the case of non-discrete groups. So at least for a circle, namely. So there exists a simple, separable, nuclear Z-stable C-star algebra, unital even. In the well, it's also UCT, and an action alpha of the circle group such that the cross product is simple but not Z-stable. Okay, so first of all, maybe let me comment on why I stress simple here. Actually, in the case of where the group is discrete, we don't have a counterexample, even if we don't assume outerness, right? So it's conceivable that for any action, the cross product is going to be Z-stable. When a group is not discrete, it's easy to give a counterexample without assuming simplicity. So it seemed clear that one needs to have some outerness condition. We do know that fine Rochel dimension would preserve the stability, and fine Rochel dimension is some sort of an outerness condition, relatively strong one. Okay, and in fact, this counterexample came about out of my failed attempt to try to prove the opposite, that basically some analog of this, that for the actions of the reals, strong outerness would somehow imply fine Rochel dimension or imply this. So I wasted a lot of time on it until I realized that I have a counterexample. So I'm glad I didn't spend more time on it. And now you won't have to waste your time on it either. So that's good. Maybe let's comment first on why did I say that simplicity is, without simplicity is trivial in this case. It's just because we take a dual action, right? And that's how I actually have this construction. So note, so without simplicity, simple, it is easy. Certainly would merit writing a paper on this. I simply take, so we take A to be a cross product. Let's say by some action beta. Okay, and these can certainly be classifiable. Take some minimal homeomorphism. This is fine dimensional. We know that the cross product is classifiable, right? And then simply take the dual action. Let's say alpha to be beta hat, the dual action. So the cross product by the circle is just going to be, by Takai duality, it's just going to be C of X tensor compacts, and this is not Z-stable. Okay, okay, I mean, that was obvious to begin with. I didn't waste time on this, but then the question is, well, would outerness be enough, or the suitable version of outerness? As I said, I didn't write the suitable version of outerness is what's called full strong Kohn spectrum. It's not important what the definition is because it's equivalent to saying that the cross product is simple. That's in the paper of Kishimoto, where he introduced that basically to give the correct some spectral condition for what's needed to get simplicity. Okay, so what I want to do with them, this preprint is actually fairly short, so I'll just give the I'll outline the idea of the proof. It's fairly simple, and mention some open questions, and then we can have coffee. So. That's a plan, unless any objections to that. Okay, so here's the idea of the proof. And I'm essentially going to give you the full idea. I mean, everything else is just checking details, or I mean, you need to be modulo Wieland construction, which is not very complicated either when you understand it. So okay, so it's essentially the same situation, right? I mean, if you look at this trivial example, right? What we start with is an action on in this case, we started with an action on C of X. C of X is not z-stable because it's commutative, right? We form a cross product, which gives us something z-stable, and then we take the dual action, we get back to something non-z-stable. But we just need to start with something which is classifiable, right? So we want to replace C of X by something which is simple but not classifiable, right? Okay, so we want to construct. So we want to find, right? And at least conceptually, it's a bit easier because it's kind of hard to think about how to make something not z-stable, right? It's kind of hard to prove that, but making something z-stable, we have technology for that. So, and we have technology for constructing non-z-stable things. So if you can somehow find a non-z-stable thing and make it z-stable, then now we know how to go back. So it's essentially the same question of can we and actually maybe phrase like that, it makes it seem that this conjecture or this idea that this class would be robust seems less reasonable because asking because if you phrase like this, can we take one of those let's say one of those guys and bring it back here, then we can hop back in this direction, right? And maybe so I mean, if there are holes in the fence, they go in both ways. So we construct a simple separable unital nuclear, in fact, an AH algebra, C-star algebra, B, and an holomorphism beta such that the cross product is z-stable, right? Okay, so if we can do that, we take the dual action and we're done. Okay, so how do we construct non-z-stable, basically those kind of types of counterexamples? They all go, I mean, there are two types of construction of Wieland. We're using the one they understand better. And they all go back to basically those two papers of Wieland. I mean, I think all the known counterexamples are some variation of one of those. And so you have something like, so there is a Wieland construction. where what you do is you take some inductive system. And in the simplest case, I mean, there's some variations of that. You can make those spaces contractible, but the simplest way to understand is to take X to be some products of spheres. So maybe X0 would be S2, and each X1 would be some X0 to the power of, let's say, of D1, and so on, right? So Xn would be, I guess, Xn to the power of Dn plus 1. So we wrote it here where you have some sequence Ds which would increase rather rapidly, right, compared to some other parameters. And we'd have those, I mean, so you'd have those parameters, the Ns, you have the Ds, you have to somehow play with them correctly. And the kind of maps which go from here to here are going to be some number of coordinate projections. So, I mean, for example, here I just took D1, a copy of D1 product, a product of D1 copies of the sphere. So we'd have the projection into each coordinate, right? So F would go to F compose the projection onto the first coordinate, second coordinate, until the this dth coordinate, and then if I only do that, I'm not going to get anything simple, right? So then I need to put here something which is intended to make it simple, right? So some point evaluations, for example, if of, let's say, some point, let's say X0, right? And it doesn't have to be one point. I can take a number of point evaluations. I can do something more complicated than point evaluations, but I need a certain number of maps here, which actually, it turns out, doesn't really matter what they are, which are just there to make the inductive limit simple, right? So to make the inductive limit simple, what you need to do is to make sure that any element here, I mean, these things are very far from being simple, would become full, meaning non-vanish at some point later on. So if you evaluate at points and you make sure that those points are somehow reasonably dense, that's going to work. There are other ways to do it. It doesn't matter. So, right, and then there's some sort of computation involving Chern characters, which show that, you know, some property of a non-stable K theory, which we're interested in this case would be perforation, would in K0 would make it to the limit, right? That was Philipson's original construction, right? You need to make those Ds grow much faster fast compared to those Ns. That's relative. That's somehow important, right? And or sorry, the dimension of those spaces would have to grow relatively fast, and then, you know, okay, there's some flexibility in this construction, but if you get those parameters correctly, then you can make sure that the inductive limit is simple and not, for example, in this case, K0 would be perforated. Okay, this is not a counterexample to the Elliott conjecture exactly, because you need to find two of those with the same Elliott invariant, which are not isomorphic, and it's too difficult to figure that out. But so the idea of Andrew Tomes was to somehow push that obstruction from K0 to the Kuhn semigroup, which is not part of the Elliott invariant, and that's how we got the counterexample. So this is the idea, right? Remember, we can put several point evaluations here as long as there are relatively few of those compared to this D, and relatively few is something you can make precise. Okay, so I'm certainly not going to go into the parameters, but that's something which is, you know, it's, once you understand its Philipson construction, you have a machine that you can use. Okay, now the problem is that, okay, so you could look at this kind of thing, right, which is a starting point for our construction, and we might want to, and then we want to construct an automorphism of that the cross product is stable. Now, okay, that's a nice idea, but I mean, I don't really know how to construct any automorphism of this, which are not trivial. I mean, it can, you know, okay, you can kind of understand why K0 is unperforated, but to actually construct to understand the automorphism group of that's not that fun. So or I have no idea how to do it. So we need to somehow have some version of this where we can actually have not only have automorphisms that we can somehow describe, but ones where you can also say something intelligent about. For example, we want the cross product to be Z stable, right? Okay, so Okay, so there's some we're proving some other paper which says that if suppose A is separable in unto, we don't really need unto, but so we phrase it, and suppose alpha is an automorphism of A which has a Rochen property, and is almost periodic. For almost periodic, it means that for any finite set and for any epsilon, you can find some power of this automorphism which almost got this finite set back to where we started. Okay, then the cross product is Z stable. Okay, even if A is not. Now, what would be an example of this? So I'll give it's a thoroughly unexciting example because these things are understood for far more complicated things without those conditions. But a nice example to have in mind is those odometer reactions, right? Which, because we're C-star algebraic, I'll describe with the product diagram. So we take, for example, right, let's write a Brodel diagram. So it's the complex numbers into each of those are complex numbers. Okay. So, but let's list those as and so on. We can do that in a systematic way. So I'll do the binary odometer, right? And think of those as being listed by, let's suppose that this is like Z mod 2, and this is Z mod 4, and so on, right? Okay, parameterized like that. Where some of the way we map this to this would be to simply take the this group element mod 2. Okay, so sorry, right? So right, we have surjective map from here to here, and okay, so we have an order 2 flip here, right? We can flip those two. Then we have an order 4 automorphism here, which is consistent with these two, right? So we can draw this, right? This would I mean, we can do it consistently, but for example, this would go here, and then this would have to go here, this goes here, and this goes here, okay? Depending on how I label them, and you can continue, right? Okay, so we'd have an order 8 automorphism here, which is consistent with this one, so on and so forth, right? The inductive limit here is the Cantor set. And you have this almost periodic action length. Why? Because, for example, anything in this subalgebra at this level, right, the C plus C, the thing is actually periodic, it has order 2, right? And here it has order 4, and so on and so forth, right? So any element is any finite set of elements is approximately in one of those subalgebras, and the action there is honestly periodic. Okay, so we know the cross product by odometer actions is stable. Of course, that's not exciting at all because we know that for far more general minimal homeomorphisms. Right? If you're interested, you could play with this idea and get an automorphism. There are those in Fulham algebras in the early days. There's this construction of Dix-Milans of this this type 2 factor which has property gamma but is not McDuff, and that's constructed as some group Fulham algebra. You can look at the C-star algebraic version of that. So with some trickery, you can somehow have an example of an automorphism of that weird C-star algebra whose cross product is Z-stable. If you do the phenomenon, you take the W star completion, that would give an example of an automorphism of this Dix-Milans example whose cross product is McDuff. But that's not what we're doing here. So okay, so what I want to do is take this example, which is really simple and very well understood, and that example, which is, well, and somehow merge those two. Okay, so suppose we take, and this goes back to this idea I have in paper with Chris Phillips on internal asymmetries of merging diagrams, and it was also used in some later in paper with Ali, Chris Phillips, and Golestani. So the idea is this: let's draw the same diagram for this of a binary tree, but overlay that with the Wheeler-Sim construction. Okay, and let's give those names to make things a bit easier. Let's call this I know, let's call this B0, B1, B2, just to make it easier to write. So we have here B0, and instead of having this one map, it's the same map, okay? So I'm not going to give it a name, but take this map and simply split it, right, into a direct sum of two copies. Okay, so just I just take the map into the two summands, then I keep on going. And so on and so forth. Okay, so I could do that, and I can do the same automorphism and get the thing to be stable. Of course, that's not remotely exciting, because if I do that, I'm going to get the tensor product of this Wheeler-Sim algebra by the continuous function on the counter set, and this is just a tensor product automorphism, which is so it's trivial and that's not what we wanted. Okay, so the idea now is let's modify this to make it simple, right? So if we look at this map, let's think of the let's draw these in two colors. Suppose let's make this yellow and this red. Okay, so think of this being essentially two arrows. There's a yellow arrow and a red arrow. Okay, the red arrow is those point evaluations. The yellow arrow is all the other stuff. So it's okay. So let's redraw this. I have here these interesting maps, right? Which are some of what's needed to get this unstable K-theory phenomenon into the inductive limit. And then I have those point evaluations, which are just there, which I have a very small number of them compared to the yellow ones. I mean, the yellow arrow is much bigger, like very thick yellow arrow and a very, very thin red arrow, right? Okay. And I have the red arrow there, which is just a matter, which is just there to make things simple. And I know that somehow we can construct the machinery that as long as I know that I don't put too many of those, then no matter how I put those red arrows, how those point evaluations, it's not going to mess up this bad behavior in the inductive limit, this perforation in K3. Okay, so here's this thing, but of course, I can add some more point evaluations, right? I mean, I can also have point evaluations going like this, right? You can put a little bit of those. So I of course have to modify those numbers a little bit to make a bit of room for it. But there's some flexibility here, right? So we'd have to make those N1s, N2s a little bit bigger, but that's okay. Okay, as long as you make this Dn grow exponentially fast, large enough, it's fine. So right, and so on, right? So I can do this, and then I can continue. I can draw the next level, but that will have lots of arrows. Okay, so I could do this, and if I did this, I simply add those point evaluations and make sure everything goes across. Now the inductive limit will be simple, right? And now it looks a lot like the previous diagram. So now what I need to do is essentially slightly modify that automorphism, right? In a way which will still make sense here, right? I can still flip those two, that's fine, right? Here, when I take an order 4 things of those, I'd have to take into account that, well, when I move things here, I also have those arrows when there. So I'd have to somehow correct that kind of picture, right? To make sure that, for example, the order 4 automorphism here is consistent with the order 2 automorphism here. That can be done. So it's not, you have to think about how to do it, but you have to conjugate by some unitaries, basically, which somehow reorder those point evaluations to make sure they work, right? But when you do that, you get a very similar situation. I mean, I have an honest order 2 automorphism here, an honest order 4 automorphism here, and so on and so forth. Okay. Now, if that happens, if I have an order 2 automorphism here, which flips those two, and an order 4 here, and so on, that's almost periodic. it also has the Rochen property. What does the Rochen property mean? It means that we have projections which gets basically moved around, right? I mean, this is a very strong version of the Rochen property. In this case, I actually have the identity of this, and this, right? And they get permuted, and they also need to be approximately central. But we get that, right? Because these will be central projections here, right? And so on. So when we do this, what happens is we get this Wheelson type algebra, which is kind of this modification of that thing, where unlike that case, here we actually know how to construct an automorphism which satisfies those properties, those nice properties. So the cross product is going to be Z stable. Okay, so that's basically the idea behind the proof, and the rest is just details and checking that the parameters work the way you want them. Okay, so maybe I'll just finish this with some questions. Right, don't forget anything. Yeah. So well, some questions. So first of all, you can ask, well, so this works in the stable finite case. I don't know what works in the purely infinite case. We know that in this discrete setting, awareness would be enough to show that pure infinite is preserved. So it's a different situation. But and of course, on the other hand, O infinity stability is not preserved. Let's take the gauge action on O2. The cross product is Carr algebra. So we won't expect O infinity stability to be preserved. But what about Z stability? I don't know. So is there an example? Of a circle action on O2, such that the cross product is simple but not Z stable? I assume at this point I assume yes, but I don't know. And a more general question. Which I mean, maybe it's kind of a more kind of vague research project. Is this? I mean, okay, so if we now decided that there are holes in that fence and maybe that other side of the fence is not so bad, you want to understand it. The Wheelson construction gives you something of C-star algebra which has positive radius of comparison in the sense of Andrew Thompson. So that's another invariant of which is only real interesting in the non-classifiable case. And what happens in this construction gives us an example. We start with something with positive radius of comparison, could be arbitrarily large. Radius of comparison. Radius, yeah, sorry. So, okay.
And what kind of radius of comparison?
I think you can get anything. You can get any number.
Any number? Yeah,
Yes.
okay, sure.
Yes. Okay. So it's a numerical invariant, the radius of comparison, right? And what happens here is we have an action which takes something with positive radius of comparison and brings all the way down to 0. Now, in the finite group case, there's some work of Ali and Chris Phillips, which gives you various radius of comparison between the so if the radius of comparison of A is x, then you can get anything between x and x divided by the order of the group. So the question would what would happen to the radius of comparison under actions of the integers? Let's suppose what are the possible values? Okay, so let's suppose that Okay, so we've shown that it can go down to 0, but can we get anything which is between any numbers between 0 and the radius of comparison of A? Can we get anything larger than the radius of comparison of A? I don't know. Okay.
What is the context? I mean, I thought you just said it could be.
It could be 0. But I don't know if it could be like half the radius of comparison of A, or could it be twice the radius of comparison of A?
What is A supposed to be?
A is the, let's say, a simple.
Or cross product?
Yeah, simple, separable, unital. Let's say if you want nuclear, I don't know if that's relevant. Okay. So I mean, okay, so we know that something can happen. We can start with something which has positive radius of comparison, form a cross product, gets 0. What else could happen? I mean, it seems plausible that you can get anything between 0 and the radius of comparison of A. But that's not a theorem, and I have no idea how you can go up, if that's even possible. So that's just a vague question. And maybe just one last remark. Okay, I mean, this doesn't really tell us anything, I think, about the discrete case, group case, right? I mean, it's this is certainly works for the circle. I don't know what happens for the reals. I expect that the same thing happens, but the construction would be more complicated, so I don't know how to do it. But I would guess it surely we should have examples of the reals such that the cross product is not z-stable and simple. But one thing we could notice is if we take a dense copy of the integers inside the circle, let's say irrational angle, right? Then okay, the cross product of that may well be z-stable, and most likely is, but the fixed point subalgebra is the same. So this does give you an example where you have an action of the integers on a classifiable C-star algebra such that the fixed point subalgebra is simple but not z-stable. Okay, the fixed point subalgebra behaves differently in the cross product, so it's not a counterexample or anything, but it's just a curiosity. So okay, let's end here.